Hello everyone, Professor Dustin here, and this video is going to be continuing to talk about work, energy, and forces, specifically conservative versus non-conservative forces. So first I want to convince you that there's two different kinds of forces in the world. First, let's consider the force of gravity, and I'm going to draw a little picture of somebody throwing a ball off a building. So if they simply drop this ball, the ball will have a path like that and fall down to the ground. Whereas if they throw it upwards at an angle, the ball will do something like that and then land. So the force of gravity acting on this ball is going to be the same no matter how they throw it, right? They throw it up here, the force of gravity will be exactly the same the entire way. They drop it, force of gravity will be exactly the same the entire way. In addition, the change in potential energy of the ball will be the same because it's dropping the same distance. Specifically, the change in the potential energy will be minus mgh. That's because the potential energy is decreasing as it goes from the top down to the bottom. So what's special about that is that the force of gravity is constant, but the change in the potential energy is the same. The change in the energy of the system does not depend on which path it takes. Specifically, the work that the gravitational force is doing on the ball does not depend on which path it takes. It satisfies this condition of path independence. So that's exactly what it sounds like. The work done by gravity on this system is path independent. It does not matter what the path of the object is, the work is the same. So that's one kind of force. The other kind of force satisfies the opposite condition. The path does matter. So the key kind of force there is friction. So let's consider pushing a box across a surface. If I push it in a straight line, the friction does some amount of work to it as it travels along that straight line. But if I push it in some other complicated path, then the work due to friction will be different because at every single point, the friction might be constant. But if I push it along a longer path, then the amount of work done by the frictional force is bigger. So friction satisfies what's called path dependence. That is, the work done depends on what path is taken. Longer path, more amount of work. So those are the two different kinds of forces in the world. Some which the work done does not depend on the path taken, and some in which the work done does depend on the path taken. This is called a conservative force. And this kind is called a non-conservative force. And so every force falls into one of these two categories. So why does this categorization matter? Well, for one, it's sort of interesting that there's obviously some kind of special feature of this kind of force that makes it not depend on the path, and this kind of force which does. But for our purposes, we want to know how do we solve problems using this, this splitting of the forces. So in order to answer that, we need to look at the work-energy theorem. So the work-energy theorem says that the change in energy of a system is equal to the work done on it. Typically, we write the change in energy split into two parts. The kinetic energy and the potential energy is the work done. So how do we take these two forces and incorporate them into the conservation of energy equation? Well, the tricky thing about forces which do not depend on the path is that you can write a potential energy for them. You can write that the change of potential energy due to gravity is minus mgh. It does not matter what path that this object takes, the change in potential energy will always be like that. And so for a conservative force, you can always write change in potential energy. And that means that all your conservative forces are going to be put into this delta U. Are going to go in there. So anytime you have a conservative force, you can determine what the potential energy is, and they can go into there. All your non-conservative forces, okay, you can't write changes in potential energy because that change implies a final and initial. But if it depends on how the object gets from the initial to the final point, you can't simply write delta U and have it work every time. So you need to go through and calculate the work. The work done by that force depends on the path taken, and you have to calculate it individually for each individual situation, which means that all your non-conservative things are going to go in this work for it. So this expression now becomes very, very powerful. So if we're given a physical situation with interactions that are described by either forces or interactions which are described by energy, we can always use this expression provided we can split the forces into conservative and non-conservative types. Take all our conservative forces, put them here, take all our non-conservative forces, put them here, and then we can solve the problem. In fact, we can even do more. If there are things that we know how much energy is contained in that interaction but don't know anything about the force, a good example of this is sound, right? So in a car crash, a lot of energy is lost via sound. We know this because we can do the measurement. We can check to see how much energy is lost. We don't know anything about the force associated with that sound, but using the Work-Energy Theorem, we can put in the energy lost or gained to sound in here, and even without knowing what the force is, we can still figure out the change in potential energy due to that sound. So it really allows us to solve a great number of problems in physics by considering these kind of energy techniques. And that's what we're going to be practicing with in class, splitting in conservative, non-conservative forces, and also working with this expression in general to solve a great number of problems. Okay, great. That has been an introduction to conservative and non-conservative forces. Thank you for watching, and I will see you next time.